In this video, you'll learn about proportional reasoning. In your child's Math 8 classroom, this means ratios, rates, and percent. Proportional reasoning is the foundation of the mathematics your child will learn in the higher grades. For example, when they learn about slopes and lines, scale diagrams, unit conversions, and trigonometry. In everyday life, people use proportional reasoning to find unknown quantities, say scaling a recipe, to make comparisons, say determining the better buy, or to make predictions, say estimating how long it will take to run or drive a distance. We will begin by exploring proportional reasoning. We encourage you to watch this video with your child and invite you to participate by pausing the video when prompted. Let's get started. Consider this pile of blue and red counters. How might you compare the number of blue counters to the number of red counters? Describe this comparison in as many ways as you can. You might have thought about the quantities in absolute terms. There are 4 more blue counters than red counters. This is called additive thinking. This thinking is valid, but not part of proportional reasoning. Instead, you might have thought about the quantities in relative terms. For every 12 blue counters, there are 8 red counters. This is called multiplicative thinking. Proportional reasoning involves thinking about multiplicative relationships between quantities. This relationship can be expressed as a ratio and written as 12 to 8. This is called a part-to-part ratio. Eight to 12 represents a different part-to-part ratio, the number of red counters to the number of blue counters. When writing ratios, order matters. Let's revisit the collection of counters. What do you think 12 to 20 represents? What comparison is being made? "12 to 20 represents the number of blue counters to the total number of counters. This is called a part-to-whole ratio. Ratios can also be written as fractions. More on this later. Let's first revisit the part-to-part ratio 12 to 8. Earlier, you might have noticed that for every 3 blue counters, there are 2 red counters. This ratio is equivalent to the ratio 12 to 8. You might spot some more equivalent ratios in the collection of counters, like 6 to 4, or 9 to 6. Notice how the number of blue and red counters change together each time the rectangles grow larger. Earlier, you were invited to compare the number of blue counters to the number of red counters. There are many ways that you might have described this proportional relationship. Press pause now and see if you see one of your ways here. Now we'll explore some strategies for finding an unknown value in a proportional relationship. Later, we'll apply these strategies to solve real-world problems. Let's stick with the same ratio. For every 3 blue counters, there are 2 red counters. How many red counters would there be if there were 45 blue counters? Use your intuition. We'll use a variable, n, to represent the unknown number of red counters. You might have noticed that 45 is a multiple of 3. Multiplying 3 blue counters by 15 gives 45 blue counters. This same scale factor is applied to the red counters. Multiplying two red counters by a scale factor of 15 gives 30 red counters. There are many strategies for solving this problem. Whatever your child's strategy, it is important that they reason proportionally. Applying memorized procedures, like cross multiplication, will not help your child to develop this ability. Remind them it's all about relationships and encourage them to look for these relationships between quantities. Let's apply what we've learned about proportional reasoning to some sample problems from the textbook. Diana and John are making 3-cheese lasagna. The recipe calls for 100 grams of Romano, 300 grams of mozzarella, and 250 grams of ricotta. What amounts of Romano and ricotta do you need to make a lasagna that contains 900 grams of mozzarella cheese? Because the recipe calls for 3 types of cheeses, we write the relationship as a 3-term ratio. There is a relationship between the 2 different amounts of mozzarella. The amount that Diana and John are using is triple the amount in the recipe. This same scale factor is applied to the Romano. And the ricotta cheese. There are multiple ways to solve this problem. These ways depend on spotting relationships between the quantities. What other relationships can you find? You might have noticed a relationship between the amount of Romano and mozzarella in the recipe. The amount of mozzarella is triple the amount of Romano. We can apply this relationship to the larger lasagna. Similarly, you might have noticed a relationship between the amount of Romano and ricotta in the recipe. The amount of ricotta is 2 1/2 that of Romano. Again, we can apply this relationship to the larger lasagna. The ratios between the kinds of cheese remains the same. 2 brands of canned dog food are on sale. The cans are the same size. Brand A costs $13.60 for 8 cans. And brand B costs $8.75 for 5 cans. Explain how you can compare the costs of the 2 brands of dog food. Determine the better buy. How would you determine the better buy? Can you figure this out in more than one way? One strategy is to divide the cost by the number of cans for each brand. Brand A costs $1.70 per can. Brand B costs $1.75 per can. Brand A is the better buy. This strategy makes comparing brands easier because 2 terms are the same, 1. This is called a unit price. But we don't have to make the number of cans 1 to make comparing brands easier. What matters is that the number of cans for each brand is the same. Here, that's 40 because 40 is a multiple of both 8 and 5. We can write a proportion to express the relationship. A proportion is an equation that says that 2 ratios or rates are equivalent. To make the number of cans for brand A equal to 40, we multiply 8 cans by 5. Applying this same multiplier to the cost, $13.60, gives $68. To make the number of cans for brand B equal to 40, we multiply 5 cans by 8. Multiplying $8.75 by 8 gives $70. Because the number of cans for each brand is the same, determining the better deal is easier. Delia runs 300 meters in 36 seconds. How long will it take her to run 1,000 meters? We'll assume that Delia will continue to run at the same speed, or rate, over the longer distance. Again, we can begin by writing a proportion. Alternatively, we can use a table of equivalent ratios to help organize the information. In this video, we'll show both representations. 1,000 meters is 3 1/3 times longer than 300 meters. Multiplying 36 seconds by this same scale factor gives 120 seconds. To find the scale factor, we can divide 1,000 meters by 300 meters. This scale factor makes sense because 3 300s make 900, and a third of 300 is 100, and 900 and 100 make 1,000. There are strategies where the computations are much easier to make. For example, dividing 300 meters and 36 seconds by 3 gives an equivalent rate of 100 meters in 12 seconds. This is helpful because both 100 and 1,000 are powers of 10. 100 meters multiplied by 10 is 1,000 meters. 12 seconds multiplied by 10 is 120 seconds. Next, we'll discuss a common mistake. Some students might incorrectly apply additive thinking to a situation where a proportional relationship exists, like the lasagna recipe problem. The difference between the amount of mozzarella Diana and John are using and the amount in the recipe is 600 grams. Applying this same difference to the amount of Romano would mean that you'd need 700 grams of Romano. Notice that the amount of Romano needed would now be almost the same as the amount of mozzarella, breaking all of the relationships that we spotted earlier. This video addresses several learning standards in the Mathematics 8 curriculum. In content, we looked at numerical proportional reasoning, specifically ratios, rates, and proportions. In Math 9, your child will learn about spatial proportional reasoning. Several curricular competencies may emerge as your child learns and applies the content from this chapter. Throughout this overview, we modeled strategies your child might apply to solve problems in both abstract and real-world situations. Note that the goal of this curricular competency learning standard is not to have your child solve every problem in multiple ways. Instead, the goal is flexibility. Your child may move between strategies based on the numbers at hand. You justified the decision of which is the better buy when you used mathematics to make comparisons.